I had a thought, but not at 3 a.m. If a picture is just data, can I listen to it? A digital photo is just a bunch of pixels, and a digital audio file is just a bunch of frequencies. Technically, they are the same thing. They are just data. I built a program to find out. Now, the tool lets me turn an image into what's called a spectrogram, which is just a visual representation of sound. And once I play it using a visualizer, I can get to see the corresponding image. I don't want to talk about the code in this video, so I will try and use an analogy instead. Just think about a piano. On this black screen, the bottom is the low notes or the bass. The top is the high notes or the treble. And time just moves from left to right as I draw. Now, there is one more rule before we continue, and that is brightness. A bright yellow pixel is a loud sound. A dark pixel is quiet. Black is total silence. Now, from our piano example, there is a catch. This isn't a normal piano. It's some sort of a linear piano. This is the most important part that you have to understand. In a real piano and in human hearing, our sense of pitch is logarithmic. To go up one octave, you have to double the frequency. The jump from 100 to 200 Hz is an octave, and the jump from 1000 to 2000 Hz is also an octave. To our ears, those are equal steps, but to a computer, it just sees the raw numbers. It thinks the jump from 1000 to 2000 is 10 times bigger than the jump from 100 to 200. Now, so on screen here, the computer maps the frequency evenly. That means the entire range of musical bass and melody, or all the notes on a guitar, are cramped into this tiny sliver right at the bottom of the screen. Now, the above region is all the high-pitched hiss. It's like the dog whistle zone. Frequency so high that they sound more like static than music, but it's not the actual dog whistle zone. So, if I draw a line way down here, it should be a low, bassy note. But what happens if I draw right here in the middle? Visually, it looks balanced, but based on our rule, it's not in the musical part of the screen. To our ears, this is actually incredibly high pitch. And if I draw anywhere else, I'm basically composing a song for bats. Okay, now I wanted to see what happens when we try to actually draw something. Now, if I draw a smiley face, logically, a smile is just a curve. So the pitch should go from high down to a lower mid-range and then back up. But the eyes are just dots, so they should be quick beeps that blend in with the smile sound. Let me play it so you can hear it. It sounds terrible. Since I drew the face in the middle of the screen, I basically composed a song entirely in the high-frequency static zone. But it is accurate. That noise is the drawing. The sound did exactly what the drawing told it to do. Enough with the abstract drawings. Let's try a real photograph. Now, I have this picture of a Volkswagen Beetle, and we're going to try and hear what it sounds like. The sound plays from left to right. At any single moment, the sound is a vertical slice of the car's shape. Now, think of it like a chord made up of all the bright pixels from the road to the roof. As the sound moves across the image, the shape of that chord will change and the volume will also change based on the car's bright and dark spots. It's not a single tone. It's a dense and complex sound because the car is a detailed object. It's thousands of pixels turned into thousands of frequencies, all playing at once. But you can hear the overall pitch rise and fall as the sound scans over the car's curved body. But I wanted to prove that the data is actually there. If I take that audio file and feed it back into the analyzer, which is a part of the tool that I built, I should be able to see the version of the car again. And as you can see, it looks like a ghost of the Beetle. I call it a ghost because the conversion process isn't perfect. Some detail is always lost. It's like making a photocopy of a photocopy, but the shape is undeniably there. So I added one feature to this program that is present in most professional analyzers, which is an option for a logarithmic scale. Now, this button transforms the view from the computer's linear world into our human logarithmic one. When I select this option, watch what happens to the car. It gets squashed and distorted. This visual change actually confirms the whole theory about the difference between a linear grid and how we actually perceive sound. And after all of this, I wanted to experiment with one last thing, and that is to write text into the canvas and get to see how that actually sounds. So I wrote the word hello. And as you can see, the letters are just simple lines. An H is just two vertical lines and a cross in the middle. Now this should make a much more cleaner and a more distinct sound than the noisy, detailed car. Now you can't hear the word hello, you can only hear the individual shapes. The sound has a form of a texture that matches its actual drawing. The H has those two sharp vertical lines with a quieter bridge in the middle. Now because letters are simple shapes, they will make simple sounds, and they become very distinct. This was another one of my projects and research about data, and it was quite intriguing if I might add. And I was wondering if you could compose music with something like this. Well, maybe, but to me, it was just an interesting way to think about data. I will try more stuff with audio in the near future, but I'm not sure where it will actually end. Thanks for watching, and I'll see you in the next one.